Welcome back. Today we step into one of the most awe-inspiring and terrifying forces on our planet, volcanoes. For as long as humans have lived in their shadow, volcanoes have inspired fear, reverence, and wonder. They are mountains that breathe fire, reminders that the earth beneath our feet is alive and restless. As we explore their story, I'd love to hear your thoughts. Which volcano fascinates you most, or which eruption in history stands out in your mind? Share it in the comments, and if you enjoy these deep journeys through science and history, consider subscribing so you can join us for the next one. Volcanoes are among the most powerful forces shaping Earth. They are both creators and destroyers, sculpting landscapes, altering climates, and reshaping life itself. To understand volcanoes is to understand Earth, for their story begins with the planet's very birth. Over 4.5 billion years ago, Earth was forged from collisions of dust and rock, a molten sphere battered by impacts. Its surface cooled, forming crust, but beneath, heat remained. Volcanoes were Earth's first exhalations, venting gases, forming continents, and perhaps even preparing the conditions for life. The atmosphere we breathe today owes much to those ancient eruptions. Carbon dioxide, nitrogen, water vapor, and other gases released from the planet's interior gradually form the air that shields and sustains us. The greenhouse effect warmed the young Earth, while rain condensed into oceans. Without volcanic outgassing, Earth might have remained barren and frozen. Even now, volcanoes continue to recycle gases and elements, linking Earth's crust, mantle, and atmosphere in a cycle as old as the planet itself. But what exactly is a volcano? At its simplest, it is a vent through which molten rock, gas, and ash escape from Earth's interior. Yet the variety is staggering. Some rise as symmetrical cones, built layer upon layer of lava and ash. Others sprawl as vast shields, their slopes so gentle they are almost invisible, yet their bulk immense. Some erupt in cataclysms that darken skies across continents. Others release steady rivers of molten rock, flowing silently but inexorably. This diversity reflects the diversity of Earth's interior processes. Different magmas, different tectonic settings, different stories. Beneath them lies magma, molten rock born of heat and pressure deep below. Magma rises because it is lighter than the solid rock around it. Its chemistry shapes its behavior. Thin, fluid magma flows quietly, while thick, sticky magma traps gases until pressure forces explosive release. A volcano's character, whether gentle or violent, is written in the chemistry of its magma and the setting of its birth. Tectonic plates provide the stage. At mid-ocean ridges, magma rises as plates diverge, building new seafloor in a near-continuous volcanic process. At subduction zones, one plate slides beneath another, melting and fueling arcs of explosive volcanoes. In the middle of plates, hotspots push plumes of heat toward the surface, creating chains of volcanoes as plates drift above them, like the Hawaiian Islands. Each setting gives rise to its own kind of fire mountain, from sprawling shields to towering stratovolcanoes. For ancient peoples, volcanoes were not geological phenomena, but divine presences. The Greeks imagined Hephaestus working his forge beneath Mount Etna. In Hawaii, Pele, goddess of fire, was honored and feared as she reshaped the land. With lava flows, indigenous cultures around the world wove volcanoes into myth, seeing them as portals to underworlds or messengers of gods. Even today, when we understand magma and tectonics, standing before a smoking crater evokes awe that feels almost sacred. And volcanoes are not only symbols, they shape human life directly. Ash, once deadly, becomes fertile soil, feeding millions. Civilizations have risen on volcanic slopes, nourished by their bounty, even as they risk destruction. Cities such as Naples, Quito, and Kagoshima live in their shadows, always balancing danger and reward. The paradox of volcanoes is clear. They are destroyers but also givers. When they destroy, the force is overwhelming. Explosions can bury towns, collapse roofs under ash, and blot out the sun. Pyroclastic flows, torrents of searing gas and rock, race faster than any human can run, obliterating everything in their path. Lahars, volcanic mudflows, sweep through valleys, swallowing entire villages. Ash clouds, ground plains, disrupt trade, and spread across hemispheres. Gases poison air and water, and in some eruptions, climates themselves shift for years. Yet when they create, the results are just as profound. Volcanoes build islands in the sea, raise mountains on land, and craft landscapes of surreal beauty. They release nutrients that enrich ecosystems, recycle carbon and sulfur, and regulate planetary systems. They are reminders that destruction and creation are not opposites but partners. Without volcanoes, Earth would be silent and sterile. This is only the beginning of their story. In the parts ahead, we will venture deeper. We will explore the hidden mechanics of magma, the anatomy of eruptions, and the histories of Krakatoa, Tambora, and Vesuvius. We will see how volcanoes shape climates, influence civilizations, and remind us of our place atop a restless planet. In the next part of our journey, we will descend beneath the crust to trace magma's path, how it forms, rises, and erupts, carrying with it the memory of Earth's fiery heart. To understand volcanoes, we must travel beneath the crust, into the realm where magma is born. It is there, in the hidden interior of the Earth, that the forces driving eruptions begin. For most of us, the surface feels stable, but this stability is an illusion. Beneath our feet, rock flows, bends, and melts over spans of time too vast for human senses. The energy that fuels volcanoes comes from this restless interior, a reminder that our planet is still alive. The Earth is layered like an onion. At the core lies a sphere of iron, solid at its center and liquid in its outer shell. Surrounding it is the mantle, a vast zone of rock that is mostly solid, but capable of flowing slowly, like honey under pressure. Above that lies the thin crust, the surface upon which we live. The crust and upper mantle together form the lithosphere, broken into tectonic plates that drift slowly across the planet. It is at the boundaries of these plates, and in plumes rising from deep within, that volcanoes are born. Heat is the driver. Much of it comes from Earth's birth, trapped inside during the planet's violent formation. More comes from the decay of radioactive elements deep within the mantle. Slowly, this heat escapes, carried upward by convection. In some places, the pressure drops enough to let rock melt. In others, water carried by subducting plates lowers the melting point, triggering the birth of magma. Magma is not just liquid rock. It is a mixture of molten minerals, crystals, and dissolved gases. Its character depends on its composition. Basaltic magma, low in silica, is thin and runny, able to flow long distances. Andesitic magma, richer in silica, is thicker and more prone to trapping gases. Rhyolitic magma, with the highest silica content, is the most viscous of all, resisting flow until pressure builds catastrophically. These differences explain why some volcanoes ooze gentle rivers of lava, while others explode with devastating force. When magma forms, it rises because it is less dense than the solid rock surrounding it. But its journey is not simple. It moves through fractures, collects in chambers, and sometimes stalls for centuries. In these magma chambers, the molten rock evolves. Crystals settle out, gases bubble upward, and chemical reactions change its composition. By the time magma is ready to erupt, it may be very different from when it first formed. Pressure builds as gases try to escape. At shallow depths, water vapor, carbon dioxide, and sulfur dioxide come out of solution, just as bubbles form when a soda bottle is opened. If magma is fluid, these gases escape easily, and the eruption is gentle. If magma is viscous, gases become trapped, pressure rises, and eventually the system fails. The result is an explosion, shattering rock and blasting ash into the sky. The style of eruption is written not only in magma's chemistry, but in the balance between gas and pressure. There are three main settings where magma is generated: at mid-ocean ridges, where plates diverge, rock rises and pressure drops, allowing basaltic magma to form. This is the most common volcanic activity on Earth, though most of it lies hidden beneath the sea. At subduction zones, one plate descends beneath another, carrying water into the mantle. This water lowers the melting point, generating andesitic and rhyolitic magma, feeding chains of stratovolcanoes like those around the Pacific Ring of Fire. At hotspots, heat rises in narrow plumes from deep within the mantle, melting rock to create isolated volcanoes such as Hawaii or Yellowstone. Each setting is a window into the processes beneath our feet. The story of magma is also the story of time. While eruptions feel sudden and violent to us, they are the result of processes unfolding over thousands, even millions of years. Magma may accumulate in chambers for centuries, evolving silently. Crustal rocks may weaken gradually before giving way. Even an eruption described as instantaneous is the culmination of slow, invisible changes. Volcanoes remind us that Earth's rhythms are measured not in years, but in geological time. Our knowledge of magma comes from both science and story. For centuries, people speculated about fire hidden inside the Earth. Myths spoke of subterranean forges, of dragons, of divine punishment. Today, geophysics, seismology, and geochemistry reveal the mechanics of magma. Seismic waves show chambers beneath volcanoes. Gas emissions reveal chemistry. Satellite images track swelling and sinking as magma shifts below. We can now watch volcanoes breathe, even when they seem asleep. Yet mystery remains. We cannot descend into magma chambers, cannot watch the melting rock rise. Our understanding is pieced together from fragments, like shadows on a wall. Every eruption teaches us more, yet every eruption also reminds us how much we do not know. The interior of Earth remains a frontier, its processes vast and partly hidden. Volcanoes are the surface expression of this hidden world. They are the points where interior processes break through. Every eruption is both a danger and a danger to those nearby, a gift of information to those who study. To trace magma from its birth to eruption is to see the planet's pulse. It is to recognize that Earth is not a static ball of rock, but a dynamic, evolving body, still alive after billions of years. In the next part of our journey, we will move upward, from magma chambers to eruptions themselves. We will explore the anatomy of eruptions, from quiet flows to violent blasts, and see how each style reflects the hidden chemistry of magma and the forces beneath the crust. When magma finally reaches the surface, it reveals itself in the form of an eruption. To witness one is to see Earth's power exposed, a sudden rupture of energy that has been building silently for years, centuries, or even millennia. Eruptions are not all the same. Some unfold with slow inevitability, lava flowing steadily down slopes in rivers of fire. Others erupt with terrifying violence, shattering rock, blasting ash into the atmosphere, and leaving entire landscapes transformed in minutes. The anatomy of an eruption is as varied as the magmas that fuel them. At one end of the spectrum are effusive eruptions. These are the quietest, though quiet is a relative term, when molten rock pours across the land. Effusive eruptions occur when magma is fluid, usually basaltic, and gases can escape without much resistance. Lava fountains into the air, then flows downslope in glowing rivers that may travel for miles. The Hawaiian volcanoes are the quintessential example. From fissures and vents, lava seeps and spills, adding layer upon layer to vast shield volcanoes. These eruptions rarely kill directly, though they may destroy homes, cover roads, and reshape coastlines. They are reminders that creation can be as relentless as destruction. At the other end are explosive eruptions, driven by viscous magma and trapped gases. As pressure builds, the eruption becomes catastrophic. Rock shatters, magma fragments into ash, and the blast can loft material tens of kilometers into the atmosphere. These eruptions are sudden and deadly. Their clouds of ash can collapse into pyroclastic flows, avalanches of gas and debris that race down slopes at speeds faster than a car. Entire towns can be buried within moments, as happened at Pompeii beneath Mount Vesuvius in 79 CE. Explosive eruptions remind us of the violence locked within the earth, waiting for release. Between these extremes lies a spectrum of eruption styles, each with its own character. Strombolian eruptions, named after Italy's Stromboli volcano, are moderate explosions that occur every few minutes, ejecting glowing cinders and bombs in rhythmic bursts. They are dramatic but not usually catastrophic, offering a window into the pulsing life of magma chambers. Volcanian eruptions, named after the island of Volcano, are more violent, sending dense clouds of ash and gas into the air with forceful blasts. Plinian eruptions, named after Pliny, the younger's description of Vesuvius, are the most devastating, producing towering columns of ash that can encircle the globe. Each eruption leaves behind signatures that tell its story. Lava flows, whether smooth and ropey like Pahoho, or jagged and blocky like Aiaiai, mark the paths of effusive eruptions. Ash deposits, layered and fine, preserve the history of explosive ones. Calderas, vast depressions formed when magma chambers collapse, are monuments to past eruptions of unimaginable scale. To walk across these landscapes is to walk through chapters of Earth's memory, each layer a sentence written in fire and ash. Eruptions also shape climate. When sulfur dioxide reaches the stratosphere, it forms aerosols that reflect sunlight, cooling Earth for months or years. The 1815 eruption of Tambora in Indonesia caused the year without a summer, bringing crop failures and famine across the northern hemisphere. Krakatoa's eruption in 1883 lowered global temperatures and painted skies with vivid sunsets. Volcanoes remind us that Earth's systems are connected, that fire in one place can ripple across continents. Yet eruptions are not always catastrophic. Small eruptions can create new land, expand islands, and build fertile soils. In Iceland, eruptions along fissures have reshaped coastlines. In Hawaii, lava flowing into the sea creates new ground, black sand beaches forming where molten rock meets water. Volcanic ash, once weathered, becomes rich soil, feeding crops for generations. The same forces that devastate also sustain. To understand eruptions, scientists study them from many angles. Seismographs record the tremors that precede explosions, like heartbeats quickening before a storm. Gas sensors measure sulfur dioxide and carbon dioxide, tracking changes that reveal magma's movement. Satellites watch volcanoes from space, detecting heat, swelling, and emissions invisible to human eyes. Each eruption is both an event and a lesson, teaching us about the dynamics of Earth's crust. But for those who live nearby, eruptions are more than lessons. They are lived experiences of fear, displacement, and resilience. Entire communities have been uprooted, their homes buried or abandoned. Yet others remain, rebuilding again and again, drawn back by the fertile soil and the familiarity of place. Volcanoes are part of identity as much as geology. They shape not only landscapes but cultures. In myths and histories, eruptions have left lasting marks. The destruction of Pompeii became a symbol of mortality, frozen in ash. The eruption of Thera in the Aegean may have inspired legends of Atlantis. Krakatoa's blast echoed across oceans, its sound heard thousands of miles away. Each eruption becomes a story, retold across generations, binding geology to memory. Eruptions remind us of scale. To stand at the foot of an active volcano is to feel small, dwarfed by forces older and larger than ourselves. They remind us that Earth is not passive but alive, its interior in constant motion. We are visitors on a restless planet, fragile atop its shifting crust. And yet, through study, myth, and story, we find ways to live alongside these giants. In the next part of our journey, we will explore volcanoes as shapers of history. We will look at some of the greatest eruptions known to humanity, Vesuvius, Tambora, Krakatoa, and more, and see how their effects rippled far beyond their slopes, changing the course of civilizations and even the fate of nations. Volcanoes have not only shaped landscapes, they have shaped history. Time and again, eruptions have disrupted civilizations, altered climates, and left cultural legacies that endure for centuries. To trace the great eruptions of history is to see how geology and humanity are intertwined, how events deep within the earth can ripple outward to change the lives of millions. One of the most famous is the eruption of Mount Vesuvius in 79 CE. On a summer's day in Roman Italy, the mountain that loomed over the Bay of Naples erupted with terrifying force. Pliny the Younger, a witness from across the bay, described towering clouds that rose like pine trees into the sky, spreading ash across the region. Pyroclastic flows swept down the slopes, engulfing Pompeii, Herculaneum, and nearby towns. Thousands died where they stood, their final moments preserved in ash and pumice. For centuries, the cities lay buried, forgotten until excavations revealed streets, homes, and even food left as if frozen in time. The destruction of Pompeii became not only an archaeological treasure, but a cultural symbol of mortality, a reminder of how quickly life can be overtaken by nature's force. Centuries later, another eruption dwarfed Vesuvius in scale. In 1815, Mount Tambora in Indonesia exploded in the most powerful eruption recorded in human history. Its blast was heard over 1,000 miles away. Ash fell as far as 800 miles from the volcano. Tens of thousands perished in the immediate aftermath, villages obliterated, crops destroyed. But Tambora's reach extended across the globe. Sulfur dioxide injected into the stratosphere dimmed the sun, leading to what became known as the year without a summer. Across Europe and North America, temperatures plummeted. Frost struck in June, crops failed, and famine spread. In New England, snow fell in July. In Europe, hunger and unrest grew, while artists and writers captured the mood in dark, haunting works. Mary Shelley, trapped by cold and gloom in Switzerland, began writing Frankenstein. Tambora was not just an eruption, it was a turning point in climate, culture, and memory. Between these two, in 1783, Iceland's Laki fissure erupted in a catastrophe that reshaped Europe. For 8 months, fountains of lava poured from the ground, releasing vast amounts of sulfur dioxide. A haze spread across Europe, dimming sunlight, cooling temperatures, and poisoning crops. In Iceland, livestock died in droves, and famine killed a quarter of the population. Across the continent, strange weather led to food shortages. Some historians argue that this crisis contributed to unrest that eventually fueled the French Revolution. Here, too, we see how volcanic events ripple into political and social upheaval, changing history far beyond their slopes. Krakatoa, in 1883, offers another lesson. Situated in the Sunda Strait of Indonesia, it erupted with a violence that stunned the world. The sound of the blast was heard 3,000 miles away, the loudest recorded in human history. Tsunamis generated by the explosion killed tens of thousands. Ash darkened skies worldwide, and sunsets glowed red for months. In the newly connected world of telegraphs and newspapers, Krakatoa became one of the first truly global news events. Reports spread almost instantly, shaping international understanding of natural disasters. It demonstrated not only the destructive power of volcanoes, but their ability to connect humanity in shared awe and fear. More recently, Mount St. Helens erupted in 1980 in Washington state. Though smaller than Tambora or Krakatoa, it was devastating in its own way. A massive landslide, the largest in recorded history, uncapped the volcano, releasing an explosion that flattened forests and killed 57 people. Scientists had warned of the eruption, and monitoring efforts provided valuable data. Mount St. Helens became a turning point in modern volcanology, teaching researchers how to better predict and prepare for future eruptions. It also demonstrated how quickly landscapes can change, entire mountainsides collapsing and reforming in a single morning. These are only a few of the great eruptions that have altered history. Each reminds us that volcanoes are not isolated events, but global forces. They cool climates, spread famine, shift politics, inspire art, and advance science. They are part of the human story, just as much as wars or inventions. But the cultural legacies of eruptions extend beyond destruction. In Japan, Mount Fuji is a sacred symbol, shaping art and identity even during its long dormancy. In the Andes, volcanoes are revered as protectors and spirits. In Hawaii, eruptions are celebrated as the work of Pele, whose lava flows create new land. Volcanoes inspire as much as they terrify, embedding themselves in myth, religion, and imagination. When we study these eruptions, we see how thin the boundary is between nature and human life. A mountain sleeps for centuries, then awakens in days, rewriting the story of entire civilizations. We see how interconnected Earth's systems are, how ash in Indonesia can chill Europe, how gases in Iceland can spark revolutions, and we see how humans respond, with resilience, with adaptation, with memory. In the next part of our journey, we will leave history's chronicles to look at volcanoes as architects of climate and ecosystems. Beyond single eruptions, volcanoes influence Earth on planetary scales, regulating carbon, shaping oceans, and even driving evolution itself. Volcanoes are not only dramatic events that alter landscapes in moments, they are also long-term regulators of Earth's climate and atmosphere. To see volcanoes only as disasters is to miss their deeper role in the planet's systems. Across millions of years, eruptions and outgassing have helped set the conditions for life, balancing gases, recycling elements, and linking the surface with the deep interior. The breath of volcanoes, slow and steady, is part of the rhythm that has kept Earth habitable. Consider carbon, Life depends on it, climate responds to it, and volcanoes help regulate it. Deep within the Earth, carbon is stored in rocks, minerals, and sediments. At subduction zones, carbon-rich oceanic crust sinks into the mantle. Some of this carbon remains trapped, locked away for millions of years, but some returns to the surface through volcanoes, vented as carbon dioxide. This long carbon cycle links life, oceans, atmosphere, and volcanoes in a single system. Without it, Earth's climate would drift into extremes. Volcanoes are also tied to water. Much of the water in Earth's oceans may have come from volcanic outgassing in the planet's early history. Even today, volcanoes release vast amounts of steam. Subduction zones recycle water into the mantle, where it lowers melting points and drives new magma formation. Volcanoes are part of a planetary water cycle that stretches from deep rock to sky. But volcanoes also shape climate in more immediate ways. Large eruptions inject sulfur dioxide into the stratosphere, forming reflective aerosols. These aerosols scatter sunlight, cooling Earth for months or years. Tambora's eruption in 1815 led to the year without a summer, with crop failures across continents. Krakatoa in 1883 dimmed global sunlight and lowered temperatures. Even smaller eruptions like Mount Pinatubo in 1991 can temporarily offset global warming. In this way, volcanoes remind us that climate is not solely in human hands, but part of larger natural rhythms. Yet the influence of volcanoes is double-edged. While aerosols cool, carbon dioxide warms. Over millions of years, sustained volcanic activity can raise global temperatures. Around 250 million years ago, massive eruptions in Siberia released enormous volumes of gas, contributing to the Permian extinction, the most severe in Earth's history. 90% of marine species vanished, and ecosystems collapsed. Here, volcanoes show their power not just to cool, but to overheat the planet, altering life's trajectory. Volcanoes also shape oceans. Submarine eruptions, though hidden, are constant along mid-ocean ridges. These eruptions build new seafloor, release minerals, and fuel hydrothermal vents. At these vents, superheated water rich in chemicals spews into the deep, supporting ecosystems that thrive without sunlight. Tube worms, clams, and bacteria flourish in darkness, living off chemical energy. Some scientists believe life itself may have begun in such environments, nurtured by the chemistry of volcanic vents. In this sense, volcanoes are not only destroyers or regulators, but creators, offering niches where life begins anew. On land, volcanoes enrich soils. Ash, once weathered, becomes fertile ground. Civilizations have long taken advantage of this. Rice terraces in Indonesia, vineyards near Vesuvius, maize fields in Central America, all flourish in volcanic soils. The paradox is clear. The same eruptions that bury towns also feed generations. Fertility and danger are bound together. Over evolutionary time, volcanic activity has been a driver of change. Mass extinctions linked to volcanism cleared ecosystems, allowing new lineages to rise. The end Triassic extinction, tied to eruptions as the Atlantic Ocean opened, paved the way for dinosaurs. The end Cretaceous event, though triggered by an asteroid, was worsened by volcanic activity in India's Deccan Traps. In each case, volcanoes helped reset the evolutionary stage, shaping the path of life. But volcanoes are not only destructive forces in evolution. They also create isolated habitats. Islands formed by volcanoes, like the Galapagos or Hawaii, become laboratories of evolution. Species arrive, adapt, and diversify, producing unique forms found nowhere else. Darwin's finches, central to the theory of natural selection, evolved on volcanic islands. Volcanoes, by creating new lands, create new possibilities for life. Even human evolution may have been influenced by volcanoes. Some researchers argue that volcanic activity in East Africa shaped the environment where early humans evolved. Ash layers preserved in the Rift Valley provide timelines for fossils. Fluctuating climates, partly driven by volcanism, may have pressured hominins to adapt, fostering flexibility and intelligence. The story of humanity is entwined with the fires of Earth. Volcanoes also remind us of Earth's resilience. Though eruptions may darken skies or trigger extinctions, life returns. Forests grow on lava flows, coral colonizes new islands, and ecosystems rebuild. Over millions of years, volcanoes have destroyed and created countless times, and still Earth thrives. To study volcanoes is to see not only danger but endurance. In the next part of our journey, we will focus on the science of prediction and monitoring. How do scientists read the signals of a restless volcano? How do they distinguish between slumber and awakening? And can we ever truly predict when the next great eruption will come? For most of human history, volcanoes were mysteries. People could only watch and wonder as mountains rumbled, smoked, and erupted without warning. Myths explained them as the anger of gods or the work of spirits. Fear and reverence were natural responses because prediction seemed impossible. Today, though volcanoes remain unpredictable in the deepest sense, science has given us tools to read their signals. Volcanology, the study of volcanoes, is not only about understanding the past. It is about watching the present, listening to mountains, and trying to anticipate the future. Every volcano tells its story before it erupts. The challenge is learning the language. One of the first signs of unrest is seismic activity. As magma rises, it fractures rock, producing small earthquakes. Sensitive seismographs placed around volcanoes record these tremors, often in patterns. A swarm of quakes, especially at shallow depths, can signal magma on the move. By analyzing frequency, intensity, and location, scientists can map magma's path upward. Another signal is ground deformation. As magma accumulates in a chamber, it pushes the ground upward. Slopes may bulge, craters may widen, summits may rise. Instruments called tilt meters measure minute changes in angle, while GPS systems track movement to within millimeters. From space, satellites use radar to detect swelling and sinking. To watch a volcano breathe is to see the slow inflation of rock above hidden reservoirs. Gases offer another clue. Magma contains dissolved water vapor, carbon dioxide, sulfur dioxide, and other gases. As pressure changes, these gases escape through vents and fumaroles. Instruments measure their concentrations and ratios, revealing changes in magma depth and chemistry. A sudden increase in sulfur dioxide, for instance, can warn that magma is nearing the surface. Even the composition of air around a volcano tells part of the story. Thermal monitoring adds another layer. Rising magma heats rock and groundwater, creating hot springs, fumaroles, and sometimes visible glow. Satellites detect these changes as shifts in infrared radiation. A mountain that warms subtly may be signaling unrest long before visible eruptions occur. By combining seismic, deformation, gas, and thermal data, scientists create a fuller picture. No single sign is conclusive, but together they form a pattern. Like doctors diagnosing a patient, volcanologists look for clusters of symptoms. If earthquakes increase, slopes bulge, gases rise, and heat spreads, the likelihood of eruption grows. Even with these tools, prediction remains uncertain. Volcanoes are complex systems, and not every sign leads to an eruption. Some show years of unrest without erupting. Others erupt with little warning. The goal is not perfect prediction, but risk reduction. Recognizing heightened danger and preparing communities. Modern monitoring has saved countless lives by enabling timely evacuations. One landmark example is Mount Pinatubo in the Philippines. In 1991, decades of quiet ended as the volcano began to stir. Scientists observed earthquakes, swelling, and gas emissions. By carefully analyzing the data, they warned of a major eruption. Tens of thousands were evacuated. When Pinatubo finally exploded in June, it became the second largest eruption of the 20th century, devastating the region but sparing countless lives through preparation. Pinatubo became a model for successful volcanology, showing what careful monitoring can achieve. In contrast, Mount Nevado del Ruiz in Colombia offers a tragic lesson. In 1985, the volcano showed signs of unrest. Tremors, steam, minor eruptions. Scientists warned of potential danger, but communication broke down and evacuation was delayed. When the volcano erupted, it melted glaciers on its slopes, unleashing lahars that buried the town of Armero. More than 20,000 people died in minutes. It remains one of the deadliest volcanic disasters of the 20th century, not because it was unanticipated, but because warnings went unheeded. The tragedy of Armero is a reminder that science alone is not enough. Preparedness and trust are equally vital. Volcano monitoring today is global. Networks of observatories watch active regions, from the Pacific Ring of Fire to Iceland, from Africa's Rift Valley to the Mediterranean. Data flows in real time, analyzed by teams of scientists who track changes day and night. International collaboration shares insights because volcanoes know no borders. The goal is always the same: to give people time. Yet challenges remain. Many of the world's dangerous volcanoes are in developing regions, where monitoring equipment is scarce. Some volcanoes are remote, hidden beneath oceans or ice, difficult to study. Others erupt so rarely that patterns are hard to recognize, and even with the best technology, uncertainty persists. Volcanoes remind us that Earth is complex and our knowledge incomplete. Still, each eruption teaches us more. Instruments improve, models grow more accurate, satellites expand our reach. Scientists now experiment with artificial intelligence, feeding it decades of volcanic data to find subtle patterns humans might miss. Drones fly into plumes to sample gases. Robots descend into craters to measure heat. The frontier of volcanology is as much about technology as geology, extending our senses where it is too dangerous for humans to go. For those living near volcanoes, prediction is not abstract science, but survival. Entire communities depend on early warnings. Farmers plant crops in fertile ash soils, knowing the risk. Families build homes on slopes that may one day erupt. For them, volcanology is not distant research but a lifeline, a balance between life and danger. In the next part of our journey, we will turn from prediction to the hazards themselves. What makes volcanoes so deadly? From lava to ash, from pyroclastic flows to lahars, we will examine the arsenal of dangers volcanoes unleash, and how humans have learned, or failed, to live with them. To live near a volcano is to live with danger. Though their slopes may be fertile, their beauty inspiring, their potential for destruction is immense. Volcanic hazards come in many forms, each with its own character, each with its own way of transforming landscapes and lives. From rivers of molten rock to invisible gases, from towering clouds of ash to floods of mud, volcanoes unleash forces that can overwhelm even the most prepared communities. The most iconic hazard is lava. When people think of volcanoes, they imagine glowing streams of molten rock flowing down a mountainside. Lava can incinerate or bury everything in its path, destroying homes, fields, and infrastructure. Yet lava is rarely the greatest killer. It usually moves slowly enough for people to escape, though its advance is inexorable. Once cooled, lava hardens into rock, entombing what it covers. Entire towns have been engulfed, roads erased, coastlines redrawn. In Hawaii, lava has created new land as it pours into the ocean, steam rising as molten rock meets water. To witness it is to see creation and destruction at once. Far deadlier are pyroclastic flows. These are avalanches of hot gas, ash, and rock fragments that race down slopes at speeds exceeding 100 kilometers per hour. Temperatures inside can surpass 1,000 degrees Celsius, enough to incinerate everything they touch. They move with terrifying speed and unpredictability, leaving little chance for escape. When Mount Vesuvius erupted in 79 CE, it was pyroclastic flows that buried Herculaneum and Pompeii. In 1902, the eruption of Mount Pelée on the island of Martinique unleashed a pyroclastic flow that destroyed the city of Saint-Pierre, killing nearly all of its 30,000 inhabitants in minutes. Few hazards demonstrate the lethal power of volcanoes more vividly. Ashfall is another danger, and one that can reach far beyond a volcano's slopes. Explosive eruptions blast fine particles into the sky, where winds carry them across vast distances. Ash can collapse roofs, contaminate water, and smother crops. Inhaled, it damages lungs. Jet engines that encounter ash clouds can fail, forcing planes to divert or risk catastrophe. The 2010 eruption of Eyjafjallajökull in Iceland grounded air traffic across Europe for days, disrupting millions of travelers. Though not deadly on the scale of pyroclastic flows, ashfall demonstrates how even distant eruptions can disrupt modern societies. Lahars, or volcanic mud flows, combine the destructiveness of water and debris. Triggered when eruptions melt snow and ice, or when heavy rain mobilizes loose ash, lahars flow down valleys like rivers of cement. They bury towns, uproot bridges, and reshape landscapes. The tragedy of Armero in 1985 was caused not by lava or ash, but by lahars unleashed by Nevado del Ruiz. Entire communities can vanish under meters of mud, leaving little trace behind. Lahars can strike long after eruptions, as rainfall remobilizes ash. They are hazards that linger, waiting for storms to awaken them. Volcanic gases, though less visible, are equally dangerous. Carbon dioxide, heavier than air, can accumulate in low-lying areas, suffocating animals and people without warning. In 1986, Lake Nyos in Cameroon, fed by volcanic gases, suddenly released a vast cloud of carbon dioxide that flowed into nearby villages, killing over 1,700 people as they slept. Sulfur dioxide, another volcanic gas, irritates lungs and combines with water to form acid rain, damaging crops and ecosystems. Hydrogen sulfide, chlorine, and fluorine add to the toxic mix. Even without dramatic eruptions, gases seeping from vents can make volcanic areas perilous. Volcanic tsunamis are another hidden threat. Explosive eruptions, caldera collapses, or massive landslides can displace water, sending waves across oceans. In 1883, Krakatoa's eruption generated tsunamis that killed tens of thousands. In 2018, part of Anak Krakatau collapsed into the sea, creating waves that struck Indonesia's coasts, killing hundreds. These events remind us that volcanoes can affect not only land, but entire seas, their reach extending far beyond their craters. Secondary effects amplify the danger. Famine often follows eruptions, as ash and lava destroy crops and livestock. Disease spreads in crowded refugee camps after evacuations. Economic disruption lingers for years as infrastructure is rebuilt. Psychological trauma endures as survivors live with the memory of fire and ash. Volcanic hazards are not confined to the moment of eruption. They ripple across time, leaving scars both visible and invisible. Despite their dangers, people continue to live near volcanoes. Fertile soils, access to water, and cultural ties keep communities on their slopes. Some accept the risk as part of life, others trust in monitoring and evacuation plans. Around the world, millions live within reach of active volcanoes, their daily lives shaped by the balance between danger and opportunity. Volcanoes remind us of the limits of human control. We can monitor, predict, and prepare, but we cannot stop an eruption. We can only respond. They are forces that belong to the Earth, not to us. And yet, by studying their hazards, we learn not only how to protect ourselves, but how to respect the power of the planet we inhabit. In the next part of our journey, we will turn to volcanoes as builders. For all their destructiveness, they are also creators of landscapes, mountains, islands, plateaus, and plains. We will explore how volcanic landforms arise and how they shape the beauty and diversity of our planet's surface. For all their destructive power, volcanoes are also architects. They shape mountains, build islands, and create landscapes of extraordinary beauty. To look at Earth's surface is to see the fingerprints of volcanism everywhere, in soaring peaks, vast plateaus, hidden ocean ridges, and isolated islands. These landforms are reminders that volcanoes are not only agents of destruction, but also of creation. Perhaps the most iconic volcanic landform is the stratovolcano, also called a composite volcano. These towering cones are built from alternating layers of lava and ash, each eruption adding a new stratum. Their slopes are steep, their summits often capped by snow or glaciers, their presence commanding on the horizon. Mount Fuji in Japan, Mount Rainier in the United States, Mount Cotopaxi in Ecuador, all are stratovolcanoes. They are beautiful, symmetrical, and dangerous, capable of explosive eruptions that devastate entire regions. Their very form embodies the duality of volcanoes, majesty and menace. In contrast, stand shield volcanoes. These giants are not steep but sprawling, their slopes so gentle they can be mistaken for plains. They form from fluid basaltic lava that flows long distances, spreading thin layers over wide areas. Mauna Loa in Hawaii is the largest volcano on Earth, a shield that rises more than 33,000 feet from its base on the ocean floor to its summit, making it the tallest mountain on the planet if measured from the seafloor. Shield volcanoes are vast, patient builders, creating islands, coastlines, and new lands. Cinder cones are smaller but no less dramatic. They rise quickly, often in a single eruption, built from fragments of lava hurled into the air. These fragments, called cinders or scoria, accumulate around the vent, forming steep-sided hills. Pariquitin in Mexico is a famous example. In 1943, a farmer watched as a crack in his cornfield opened, smoke billowed, and within days a cinder cone was rising. In less than a decade, it grew to 1,300 feet high, burying villages but creating a new mountain before the eyes of those who lived there. Cinder cones remind us that Earth's landscapes can change not only over millennia, but within a single lifetime. Calderas are among the most awe-inspiring volcanic landforms. These vast depressions form when a volcano erupts so violently that its magma chamber collapses, leaving a crater miles wide. Crater Lake in Oregon, Yellowstone in the United States, and Lake Toba in Indonesia are all calderas. They can be filled with water, forests, or even entire ecosystems disguising their violent origins. Calderas are monuments to Earth's most powerful eruptions, scars left by explosions that reshaped continents and climates. Volcanoes also build plateaus and plains. The Deccan Traps in India and the Columbia River Basalt Plateau in the United States are vast regions covered by ancient lava flows. These flood basalts erupted not in towering explosions, but in repeated outpourings of lava that spread for hundreds of miles. Over time, they built thick layers of rock, reshaping entire landscapes. Though quiet compared to explosive eruptions, their long-term impact is immense. Underwater, volcanoes are even more prolific. Along mid-ocean ridges, lava wells up continuously, creating new seafloor. This process builds mountain chains tens of thousands of kilometers long, hidden beneath the waves. In some places, submarine eruptions break the surface, creating new islands. The island of Surtsey, born off Iceland in 1963, was one such event, watched and studied from its fiery beginning. Underwater volcanoes remind us that most volcanic activity occurs out of sight, shaping Earth silently in the depths. Islands formed by volcanoes have special significance for life. Isolated from continents, they become laboratories of evolution. Species arrive by air, sea, or driftwood, then adapt to unique conditions. The Galapagos Islands, the Canary Islands, Hawaii. Each hosts species found nowhere else. Volcanic islands are crucibles of diversity, showing how life can flourish on new land forged from fire. Volcanoes also create beauty beyond imagination. Lava can sculpt surreal landscapes of twisted rock, caves, and arches. Ash can paint slopes in stark colors. Eruptions can form lakes of emerald green, their waters tinted by minerals. Snow-capped peaks can rise from tropical jungles, their symmetry breathtaking. To stand before a volcano is to see both destruction and art, Earth painting its canvas with fire and stone. But volcanic landforms are not static. Erosion reshapes them, glaciers carve them, forests cloak them. A volcano may slumber, its crater filling with water, its slopes with life, until only the keen eye of geology reveals its fiery past. Some become places of pilgrimage, like Mount Fuji, revered for its form. Others become playgrounds, with hikers, skiers, and tourists exploring their slopes. What was once feared may become beloved, a reminder of Earth's resilience and renewal. Volcanoes build, destroy, and rebuild again. Their landforms are records of this cycle. Each mountain, island, and plateau a chapter in Earth's story. To learn their shapes is to read that story, to see the slow artistry of the planet beneath our feet. In the next part of our journey, we will shift from the landscapes volcanoes create to the lives they support, from fertile soils to unique ecosystems, from forests on slopes to life in lava tubes. We will see how volcanoes are not only geologic features, but foundations for life itself. Volcanoes may seem like places of death, landscapes defined by fire, ash, and destruction. Yet paradoxically, they are also places of life. Time and again, ecosystems have risen on volcanic slopes, nourished by soils that are among the richest on Earth. To study volcanoes is not only to witness devastation, but to see resilience and renewal, the ways living things reclaim ground forged by fire. When lava first cools, the result is barren rock, jagged and lifeless. At first glance, it appears impossible for life to take hold. Yet the process begins almost immediately. Wind carries spores, seeds, and insects. Lichens colonize the bare rock, breaking it down with their acids, beginning the slow creation of soil. Mosses follow, then grasses, then shrubs and trees. What was once lifeless stone becomes, step by step, an ecosystem. This process, called primary succession, shows the patience of life, its ability to make homes even in the harshest places. Volcanic soils are especially fertile because they are rich in minerals. Ash, once weathered, releases nutrients like potassium, phosphorus, and calcium. These feed plants, which in turn feed animals. Around the world, volcanic slopes support lush forests, grasslands, and farms. In Java, terraced rice fields grow on volcanic ash. In Sicily, vineyards flourish near Mount Etna. In Central America, coffee thrives in volcanic soils. Communities risk living near volcanoes, not only because of tradition, but because the land itself is generous. Volcanoes also create unique habitats. On the Galapagos Islands, born of volcanic fire, species evolved in isolation. Giant tortoises, marine iguanas, finches, all adapted to conditions shaped by lava, ash, and scarce resources. Hawaii, another volcanic chain, is home to honey creepers, silver swords, and countless plants and insects found nowhere else. Volcanic islands are crucibles of biodiversity, their isolation allowing evolution to experiment freely. Even within volcanoes, life finds a way. Lava tubes, long tunnels left by flowing lava, become homes for bats, insects, and microbes. Some tubes contain unique species found nowhere else, adapted to darkness and scarcity. Crater lakes formed in volcanic depressions host fish and invertebrates. On slopes, hot springs and fumaroles support extremophiles, microbes that thrive in boiling, acidic, or sulfur-rich waters. To life, even the harshest volcanic environments are opportunities. Volcanoes also sustain life in the oceans. Submarine eruptions feed hydrothermal vents, where superheated water rich in minerals pours from the seafloor. Around these vents, entire ecosystems flourish without sunlight. Tube worms, clams, crabs, and shrimp live in partnership with bacteria that convert chemicals into energy, a process called chemosynthesis. These vent communities are among the most alien on Earth, yet they may resemble the cradle of life itself. Some scientists believe life began at volcanic vents billions of years ago, nurtured by their chemistry and heat. Animals, too, adapt to volcanic landscapes. Birds nest on cliffs of cooled lava. Insects exploit warm ground near fumaroles. Large mammals graze on volcanic plains, benefiting from fertile grasses. In East Africa, volcanic highlands support wildebeest, zebras, and predators. In Japan, macaques warm themselves in hot springs heated by volcanic activity. Everywhere, life finds ways to use what volcanoes provide. Yet volcanoes test life with cycles of destruction. An eruption may obliterate forests, bury fields, and wipe out ecosystems. But over time, life returns, often more abundant than before. Forests regrow, animals recolonize, soils renew. This cycle of death and rebirth is part of the natural rhythm. Volcanoes remind us that ecosystems are not static but dynamic, shaped by disturbance as much as by stability. For humans, volcanoes are both blessing and curse. They destroy communities, yet they also sustain them. They provide fertile soils, hot springs, geothermal energy, and building materials. They inspire culture, art, and spirituality. People have learned to live with volcanoes, to adapt to their rhythms, to rebuild after eruptions. The relationship is uneasy but enduring, born of necessity and shaped by resilience. Volcanoes also connect us to the deep past. The first plants colonized volcanic islands, creating new habitats for animals. Early humans in East Africa lived in landscapes shaped by volcanoes, their fossils preserved in ash layers that provide vital timelines for anthropology. Our own species may owe part of its story to volcanic environments that challenged and inspired adaptation. To live with volcanoes is to live with reminders of our history. In the next part of our journey, we will look more closely at this human connection. Beyond soils and resources, volcanoes have shaped civilizations, inspired myths, and influenced cultures. They are not only geological features but cultural forces, woven into the stories humanity tells about itself. Volcanoes are more than mountains of fire. For as long as humans have watched them breathe smoke, pour lava, or shake the earth, they have been woven into stories, myths, and beliefs. Across cultures and continents, volcanoes have stood as symbols of gods, portals to other worlds, and warnings of mortality. To understand their cultural significance is to see how deeply they are etched into the human imagination. In ancient Greece, Mount Etna was believed to be the forge of Hephaestus, god of fire and metalworking. When the volcano erupted, people imagined sparks from his hammer striking an anvil deep underground. The Cyclopes, mythical giants with a single eye, were said to dwell beneath, crafting weapons for the gods. For the Greeks, Etna was not only a mountain, but a gateway into divine realms, its rumblings the echoes of immortal work. In Rome, the god Vulcan gave his name to volcanoes. He was the divine blacksmith, associated with destructive fire as well as creative craft. Eruptions were seen as his presence, reminders that fire could both build civilization and undo it. The island of Vulcano in the Mediterranean, with its steaming vents, became his mythical workshop. From Vulcan, our word volcano derives, a testament to how myth shaped language itself. In Hawaii, volcanoes are alive with the spirit of Pele, goddess of fire. She is both feared and revered, for she destroys with lava, but also creates new land. Stories tell of her battles with siblings, her temper that shapes the islands, her presence felt in glowing lava flows. Offerings are still made to her, and eruptions are seen as her will. To live in Hawaii is to live in Pele's domain, where destruction and creation are part of the same story. In the Andes, volcanoes are called apus, mountain spirits that protect and judge communities. Rituals honor them with offerings of food, coca leaves, and prayers. In Japan, Mount Fuji, though not recently active, is revered as sacred. Its symmetrical form has inspired countless artworks, poems, and pilgrimages. Even dormant volcanoes carry spiritual weight, their presence commanding reverence. For indigenous peoples of North America, volcanoes appear in creation stories and moral lessons. In the Pacific Northwest, tales describe battles between mountain spirits, their eruptions the result of anger and conflict. The eruption of Mount Mazama, which created Crater Lake, is remembered in oral traditions passed down for generations, preserving memory of an event that occurred thousands of years ago. Volcanoes are also linked to the underworld. In many cultures, craters and fumaroles were seen as portals to realms of spirits or the dead. Smoke rising from the earth was a sign of hidden worlds below. For the Maya, volcanoes were sacred sites, places of offerings and rituals. In the Philippines, Mount Mayon is tied to tragic love stories, its perfect cone said to hold the spirit of a maiden. Everywhere, volcanoes are more than geology. They are narratives, symbols, teachers. Eruptions themselves became myths. The destruction of Pompeii entered Western imagination as a symbol of divine punishment, its sudden burial echoing themes of mortality. The eruption of Thera in the Aegean around 1600 BCE may have inspired stories of Atlantis, a lost civilization swallowed by catastrophe. In Iceland, eruptions were tied to sagas of giants and spirits. Human memory transforms geological events into legends, ensuring that even when the science was unknown, the lessons were remembered. But volcanoes are not only feared, they are also sources of identity and pride. Communities living near volcanoes often see them as protectors, symbols of home. Their forms dominate skylines, anchoring landscapes in collective memory. Artists paint them, poets describe them, musicians sing of them. Volcanoes are muses as much as monsters, inspiring creativity alongside fear. In modern times, volcanoes continue to influence culture. Literature and film use them as metaphors for passion, destruction, and power. Paintings of Krakatoa's sunsets inspired Impressionist art. Tourism draws millions to volcanoes, where people climb their slopes, gaze into craters, or watch lava flow at night. The awe that once birthed myths still lives on, though now reframed through science and spectacle. This blending of myth and science is itself revealing. Even as we study magma chambers and gas emissions, volcanoes evoke emotions that transcend measurement. To see fire emerging from Earth is to feel connected to forces older and larger than ourselves. Myths may not explain the mechanics, but they capture the experience, the awe, the fear, the reverence. They remind us that volcanoes are not only geological features, but cultural monuments. In the next part of our journey, we will step back from culture to examine volcanoes on planetary scales. For Earth is not alone in its volcanism. Across the solar system, other worlds breathe fire and ash, some more violently than anything on our planet. By comparing volcanoes on Earth with those beyond, we will see how universal these processes are and how they connect us to the wider cosmos. Volcanoes are not unique to Earth. They are the natural outcome of heat, pressure, and geology, and wherever these conditions exist, volcanoes arise. To look beyond our planet is to see that fire is a universal language spoken by worlds across the solar system. Some are quiet now, their volcanic past etched into frozen surfaces. Others are alive with eruptions more powerful than anything on Earth. By studying them, we not only understand other worlds, but gain perspective on our own. Mars offers some of the most striking volcanic landscapes in the solar system. Its most famous feature is Olympus Mons, the largest volcano known. Rising nearly 22 kilometers above the Martian surface, it is nearly 3 times taller than Mount Everest, and its base would cover the entire state of Arizona. Olympus Mons is a shield volcano, formed from repeated eruptions of fluid lava that spread far and wide. Its immense size is due to Mars's lack of plate tectonics. On Earth, plates move, carrying volcanoes away from hotspots. On Mars, the crust is static, allowing lava to pile up in one place for hundreds of millions of years. Though Olympus Mons is now dormant, its scale testifies to the planet's volcanic past, when Mars was warmer, wetter, and more geologically active. Elsewhere on Mars, volcanic plains and smaller shields mark a history of eruptions. Lava once flowed across vast regions, carving channels and shaping landscapes. Though the planet is largely inactive today, evidence suggests volcanic activity continued into the recent past, perhaps as little as a few million years ago. In planetary time, that is almost yesterday. If Mars still harbors heat, hidden eruptions may not be entirely a thing of the past. On Venus, volcanoes are everywhere. The planet's surface is covered with volcanic features, shields, domes, calderas, and vast lava plains. Unlike Earth, Venus lacks clear plate tectonics, but its surface appears to have been resurfaced by massive volcanic outpourings. Vast plains of basalt stretch across continents, broken by towering volcanic mountains like Mount Mons, which rises 8 kilometers high. Some evidence suggests Venus may still be volcanically active today. Variations in atmospheric gases, hotspots detected by radar, and changes in surface features hint that eruptions could still be reshaping the planet. If true, Venus is a world where volcanoes still breathe beneath crushing atmospheres and searing heat. Beyond the rocky planets, volcanic activity takes form stranger still. On Jupiter's moon, Io, volcanoes erupt more violently than anywhere in the solar system. Io is a world of sulfur and fire, its surface painted in vivid yellows, reds, and blacks by constant eruptions. Geysers of molten sulfur shoot hundreds of kilometers into space. Lava flows across plains in rivers wider than cities. The source of Io's activity is not radioactive decay, but tidal heating. Gravitational tugs from Jupiter and neighboring moons stretch and flex Io, generating heat that melts rock. The result is a world where volcanism is constant, reshaping the surface in real time. To look at Io is to see a planet alive with fire, a reminder that volcanism can be driven by forces beyond those found on Earth. Saturn's moon Enceladus offers another twist. Instead of molten rock, its volcanoes spew water. At its south pole, geysers of water vapor, ice, and organic molecules erupt from cracks in the icy crust, feeding Saturn's E-ring. These cryovolcanoes are driven by heat from tidal forces, keeping a subsurface ocean liquid beneath the ice. Enceladus's eruptions may provide the ingredients for life, carrying water, heat, and organic material into space. They expand our definition of volcanism, showing that even ice can flow and erupt under the right conditions. Triton, Neptune's largest moon, also hosts cryovolcanoes. Voyager 2 observed plumes of nitrogen gas erupting kilometers into the thin atmosphere, driven by seasonal heating. Pluto 2 may show signs of icy volcanism, with mountains that resemble frozen shields. These eruptions are not of fire but of frost, yet they follow the same principles: internal heat, pressure, release. Volcanism, it seems, is a process that transcends composition, occurring wherever a world has energy to drive it. Studying extraterrestrial volcanoes deepens our understanding of Earth. By comparing Mars's ancient giants, Venus's widespread plains, Io's firestorms, and Enceladus's icy geysers, we see the variety of planetary processes. We learn that volcanism is not only about heat, but about context, gravity, chemistry, crust, and history. Earth is just one expression of a universal phenomenon. These discoveries also fuel imagination. To picture Olympus Mons towering into thin Martian skies, to imagine standing on Io as sulfur erupts into space, to see ice plumes spraying from Enceladus into Saturn's rings. These are visions that connect geology with wonder. Volcanoes remind us that planets are alive, not static. They remind us that Earth is part of a family of worlds, all shaped by fire, ice, and time. In the next part of our journey, we will return to Earth and look at volcanoes through the lens of deep time. Over billions of years, volcanism has not only sculpted continents and oceans, but helped shape the very evolution of our planet. To see their role in Earth's long story is to see the planet itself as a living, changing entity. Volcanoes are not just features of the present, they are threads woven through the entire history of Earth. From the planet's fiery birth to the landscapes we inhabit today, volcanism has been a constant force of creation and transformation. To look at Earth's past is to see that volcanoes have not only shaped continents and oceans, but guided the very course of life itself. When Earth first formed over 4.5 billion years ago, it was a molten world. Bombarded by asteroids, heated by radioactive decay, its surface was a sea of magma. As the planet cooled, the first crust solidified, but beneath, heat remained, and volcanoes were among the earliest features of the young Earth. Their eruptions vented gases, carbon dioxide, nitrogen, and water vapor, into the sky, creating the first atmosphere. It was not yet breathable, but it was a foundation. Rain condensed, oceans formed, and the cycle of water began. Without volcanic outgassing, Earth would have remained barren, unable to sustain the chemistry of life. In the Archean Eon, over 3 billion years ago, volcanic activity continued to shape the planet. Basaltic eruptions built the first stable cratons, the ancient cores of continents that still exist today. Hydrothermal vents at mid-ocean ridges released minerals and heat into the oceans. Around these vents, simple organisms thrived, living not on sunlight but on chemical energy. Many scientists believe that life itself may have begun in such volcanic environments, nurtured by their chemistry and protected from harsh radiation at the surface. If true, then volcanoes were not just shapers of Earth, but cradles of life. Through the Proterozoic, volcanic activity continued to recycle crust, regulate climate, and influence oceans. Massive eruptions may have played roles in Earth's great glaciations, including the Snowball Earth episodes when ice covered much of the globe. Volcanic outgassing of carbon dioxide may also have ended these freezes, warming the planet again. Here we see volcanoes as planetary thermostats, sometimes plunging Earth into cold, sometimes heating it into warmth, always balancing extremes. In the Paleozoic era, volcanoes accompanied the rise of complex life. When supercontinents like Gondwana and Pangaea assembled, vast volcanic provinces erupted as plates collided and rifted. Flood basalts poured across continents, releasing gases that altered climates and ecosystems. Some eruptions coincided with mass extinctions. Around 252 million years ago, the Siberian traps unleashed millions of cubic kilometers of lava over hundreds of thousands of years. The gases released, carbon dioxide, methane, sulfur dioxide, destabilized climate, acidified oceans, and stripped oxygen from seas. The result was the Permian extinction, the most severe in Earth's history, wiping out 90% of marine species and 70% of terrestrial ones. Volcanism was not the sole cause, but it was a central driver, showing how profoundly volcanoes can shape life's trajectory. In the Mesozoic, volcanoes again played critical roles. As the Atlantic Ocean opened, massive eruptions formed the Central Atlantic Magmatic Province, contributing to the end Triassic extinction. Later, the Deccan Traps erupted in India, coinciding with the asteroid impact that ended the age of dinosaurs 66 million years ago. The combination of extraterrestrial and volcanic forces altered climate, ecosystems, and evolution, paving the way for mammals and eventually humans. In the Cenozoic, the age of mammals, volcanic activity continued to shape landscapes. The Andes rose as the Nazca Plate subducted beneath South America, creating chains of volcanoes that still erupt today. In East Africa, rifting and volcanism created highlands, lakes, and valleys that influenced the environment where early humans evolved. Ash layers preserved in sediments provide timelines for fossils, linking our evolutionary story directly to volcanic activity. Some eruptions may even have challenged early humans, altering climates, testing resilience, and fostering adaptation. Throughout Earth's history, volcanoes have been both destroyers and enablers. They caused mass extinctions, yet they also created conditions for new life to flourish. They regulated climate, sometimes catastrophically, but often in ways that kept Earth habitable. They built continents, islands, and mountains, giving shape to the world we know. To see volcanoes across deep time is to see them as central players in the planet's evolution. Even now, volcanoes continue to write Earth's story. Eruptions may seem sudden, but they are part of cycles that stretch across millions of years. The crust is recycled, the mantle stirs, and volcanoes rise and fall. We live in one moment of this ongoing tale, a brief chapter in a book still being written. To understand our place, we must see volcanoes not as anomalies, but as continuities, threads that run from Earth's fiery birth to its present face. In the next part of our journey, we will look at volcanoes not only as geological and historical forces, but as engines of energy. We will explore how humans have learned to harness their heat, turning destructive potential into a resource that sustains modern life. Volcanoes are often remembered for the destruction they cause, but they also provide extraordinary benefits. For thousands of years, humans have drawn not only fear from volcanoes, but sustenance, inspiration, and even energy. Few natural forces demonstrate the paradox of danger and opportunity more clearly. Today, in an age of growing demand for clean power and sustainable resources, volcanoes are being reimagined not only as threats, but as allies. The most direct way humans harness volcanic energy is through geothermal power. Beneath volcanic regions, the heat of magma warms groundwater, creating natural reservoirs of steam and hot water. By drilling into these reservoirs, humans can tap the Earth's heat, converting it into electricity. The principle is simple. Water is turned into steam, the steam drives turbines, and the turbines generate power. Unlike fossil fuels, geothermal energy is renewable as long as the Earth's internal heat continues, and it will, for billions of years. Iceland is one of the most striking examples of this partnership. Straddling the mid-Atlantic ridge, the island is alive with geothermal activity. Steam vents, hot springs, and geysers dot the landscape. Icelanders have learned to use this heat for almost every aspect of life. Today, nearly 90% of homes in Iceland are heated by geothermal energy. Entire greenhouses flourish in the cold climate, warmed by volcanic heat. Pools and spas, such as the famous Blue Lagoon, use geothermal waters. In Iceland, volcanoes are not only a threat, but a foundation of daily life, making the nation one of the most energy independent in the world. Other countries too rely on geothermal energy. The Philippines, Italy, New Zealand, Kenya, and the United States all operate geothermal plants, many located in volcanic regions. In the Rift Valley of Kenya, volcanic heat powers stations that supply electricity to millions. In New Zealand, Maori traditions long used geothermal hot springs for cooking and bathing, practices now integrated into modern energy systems. Even in California, the geysers, one of the world's largest geothermal fields, provides renewable electricity, though it is fueled by heat from deep faults rather than active volcanoes. Geothermal energy is not only clean but steady. Unlike solar or wind, it is not dependent on weather. The heat of the Earth is constant, available day and night in every season. For regions with volcanic activity, it offers a sustainable path into the future. Yet it is not without challenges. Drilling is expensive, and resources are not evenly distributed. Some sites risk releasing carbon dioxide or sulfur gases if not carefully managed. But overall, geothermal energy is one of the most promising tools humans have for reducing dependence on fossil fuels. Volcanoes also provide resources beyond energy. Their eruptions release valuable minerals and materials. Volcanic soils, as we have seen, are among the most fertile in the world, feeding millions. Lava rock is used in construction, from ancient Roman concrete to modern roadbeds. Pumice, a frothy volcanic rock, is used in abrasives, filtration, and even cosmetics. Obsidian, volcanic glass, was one of humanity's first tools, used for blades, arrowheads, and trade across continents. Volcanoes have always been quarries as much as mountains, shaping economies as well as landscapes. Metals, too, are tied to volcanic systems. Hydrothermal fluids circulating near magma chambers carry copper, gold, silver, and other elements. When they cool, these elements crystallize into veins rich in ore. Many of the world's great mining regions, from the Andes to Papua New Guinea, owe their wealth to ancient volcanic activity. Volcanoes create not only mountains, but economies, their buried treasures fueling civilizations and industries. Even tourism has become a resource. Millions of people travel to volcanic regions each year, drawn by their beauty, danger, and mystery. They climb Mount Fuji, bathe in Iceland's hot springs, peer into the craters of Etna or Kilauea, or watch lava flow into the sea. Volcanoes inspire awe that transcends fear, offering experiences found nowhere else. Tourism brings both income and awareness, helping people connect with Earth's living forces. Yet these benefits come with risks. To harness volcanoes is to live with uncertainty. Geothermal plants must be carefully monitored to avoid triggering earthquakes or releasing gases. Mining near volcanic regions must balance wealth with safety and environmental impact. Tourism must respect both danger and sacred traditions, avoiding exploitation. The paradox persists. Volcanoes give, but they can also take away. For all their hazards, volcanoes offer a model of sustainability. Their energy is renewable, their soils regenerative, their resources enduring. They remind us that destruction and creation are inseparable. By learning to live with them, not against them, we find paths to coexistence. In the next part of our journey, we will step away from resources and turn back to science, to the cutting edge of volcanology. We will explore the tools, techniques, and questions that drive the field today, from drones and satellites to the mysteries of supervolcanoes. Volcanology is a science shaped by danger. To study volcanoes is to work in landscapes where the ground shakes, where the air can burn, and where destruction may come without warning. Yet it is also a science of wonder, driven by the desire to understand one of Earth's most powerful forces. Over the past century, volcanology has transformed, moving from field sketches and eyewitness accounts to satellites orbiting above, drones sampling plumes, and supercomputers modeling eruptions. And yet, despite all our progress, volcanoes still hold mysteries that remind us how much we have yet to learn. Modern volcanology is built on observation. Seismographs remain one of the most important tools. Networks of instruments encircle active volcanoes, recording tremors that reveal magma's movement. The precision of these tools has grown immensely, able to detect even the faintest microquakes deep beneath the surface. Combined with GPS stations and radar satellites, scientists can now watch a volcano swell, tilt, or sink with millimeter accuracy. Where once eruptions came as total surprise, today we can often see them coming days, weeks, or even months ahead. Gas monitoring has also advanced. Instruments now measure volcanic gases in real time, both on the ground and from the air. Drones fly directly into plumes, collecting samples too dangerous for humans to reach. Satellites detect sulfur dioxide spreading across the sky, allowing scientists to track eruptions even in remote regions. These gases not only warn of impending eruptions, but reveal details about magma's depth and chemistry. Thermal imaging adds another layer. Infrared cameras can detect heat changes invisible to the eye. Satellites pick up temperature shifts across entire volcanic regions. By watching heat signatures, scientists can identify new vents, track lava flows, and monitor activity even at night or through clouds. What was once hidden is now visible pixel by pixel from Earth and from space. Computational modeling is perhaps the newest frontier. By feeding real-time data into computer simulations, volcanologists can model how magma will rise, how ash will spread, or how lahars might flow. These models allow for scenario planning, giving communities vital time to prepare. The models are imperfect, of course, because volcanoes are complex systems with countless variables, but each eruption refines the science, adding data that makes the next prediction stronger. Yet mysteries remain. One of the greatest is the question of supervolcanoes. These rare giants, capable of eruptions thousands of times larger than typical volcanoes, leave scars like Yellowstone in the United States, Toba in Indonesia, and Taupo in New Zealand. Their eruptions can blanket continents in ash, alter global climate for decades, and threaten life on a planetary scale. Fortunately, such events are rare, occurring only every tens of thousands or hundreds of thousands of years, but their potential makes them objects of intense study. How exactly they build pressure, what triggers their eruptions, and how they might behave in the future remain subjects of debate. Another mystery lies in magma itself. We know its chemistry, its minerals, its gases, but how magma chambers evolve over centuries remains partly hidden. Do they fill gradually or pulse with sudden influxes? Do crystals act as pressure valves, or do they make eruptions more likely? Even with modern imaging, we cannot see chambers directly. We interpret their behavior through tremors and chemistry. Like doctors diagnosing a patient they cannot open. There is also the question of volcanic lightning, the spectacular flashes seen in ash plumes during explosive eruptions. The cause lies in static charges from colliding particles, but the details are still under study. These fiery storms remind us that eruptions are more than geology. They are atmospheres, weather systems born in seconds. Even the role of volcanoes in long-term climate remains debated. We know their gases influence temperature, but the balance between cooling aerosols and warming carbon dioxide is complex. Over millions of years, volcanism has both warmed and cooled Earth, sometimes driving extinctions, sometimes sustaining life. Understanding these cycles is critical as we face our own era of climate change. New technology continues to expand our reach. Robots descend into craters, measuring gases and heat. Autonomous underwater vehicles explore submarine eruptions. Virtual reality reconstructs eruptions for study and training. Artificial intelligence combs through decades of seismic data, finding patterns too subtle for humans. Each innovation brings us closer to understanding volcanoes, not only as hazards, but as systems, intricate and dynamic. Yet volcanology is also a human story. Scientists climb slopes in heavy suits, risking toxic gases to collect samples. Pilots fly into ash plumes to test instruments. Local communities partner with researchers, sharing knowledge passed down through generations. In places like Indonesia, Japan, and the Andes, volcanology is not only science but tradition, woven into daily life. Volcanoes remind us of humility. For all our tools, we cannot control them. We can only listen, watch, and learn. Each eruption is both a tragedy and a classroom, teaching lessons at great cost. As our technology improves, so does our ability to live alongside volcanoes, but the mystery remains. They are forces larger than ourselves, reminders that Earth is still alive, restless, and powerful. In the next part of our journey, we will look at volcanoes through the lens of the future. As populations grow, as climate changes, as technology advances, what role will volcanoes play in the centuries to come? Will we learn to coexist with them more safely? Or will they continue to surprise us with their power? To think about volcanoes is often to think about the past, the eruptions that buried cities, the flows that carved valleys, the legends passed down through centuries. But volcanoes also belong to the future. They are not relics, they are ongoing processes, reminders that the Earth we know today will not be the Earth of tomorrow. As human populations expand, as technology changes, and as the climate shifts, the relationship between people and volcanoes will enter new and uncharted chapters. The first reality is that many of the world's largest cities now lie within reach of active volcanoes. Mexico City, home to tens of millions, lives in the shadow of Popocatépetl. Naples, with over 3 million people, lies near Vesuvius and the restless Campi Flegrei caldera. Jakarta, Manila, Quito, and Tokyo are all close to volcanic hazards. Unlike in the past, where eruptions devastated towns or regions, future eruptions may directly affect megacities, with consequences on unprecedented scales. Evacuating thousands is hard, evacuating millions is nearly impossible. The stakes have grown. Globalization magnifies these risks. Modern economies depend on fragile networks of trade, transport, and communication. An ash cloud in Iceland in 2010 grounded flights across Europe, costing billions. That eruption was relatively small. A larger one could disrupt air travel worldwide, halting supply chains and isolating nations. Ports near volcanoes may close, shipping may stall, and digital infrastructure may falter if key cities are struck. In the modern world, volcanic eruptions are no longer local events. they are global shocks. Climate change adds another layer of complexity. Melting glaciers on volcanic mountains reduce pressure on magma systems, potentially increasing activity. Warming oceans may alter the stability of submarine volcanoes. Changing rainfall patterns can remobilize ash deposits, triggering lahars decades after eruptions. At the same time, volcanic aerosols may temporarily offset warming, cooling the planet after major eruptions. The interplay between volcanism and climate is dynamic, and in the coming century, the two will interact in ways we are only beginning to understand. Technology, however, also offers new opportunities. Advances in monitoring allow for earlier warnings, more accurate predictions, and better preparation. Satellites provide global coverage, ensuring that even remote volcanoes are watched. Drones and robots venture where humans cannot, gathering data from craters and plumes. Artificial intelligence analyzes patterns across vast datasets, identifying signs of unrest faster than human eyes alone. The tools of volcanology grow more sophisticated each year, increasing our ability to coexist with Earth's fire. Geothermal energy may play an even larger role in the future. As societies transition away from fossil fuels, volcanic regions offer renewable, reliable power. Entire nations could heat and light their homes with Earth's internal energy, as Iceland already does. Even in non-volcanic regions, enhanced geothermal systems aim to replicate these conditions by drilling deep into hot rock. Volcanoes, once feared as destroyers, may become cornerstones of sustainable futures. Yet we must also confront the possibility of super eruptions. Though rare, their impact would be global. An eruption on the scale of Toba, Yellowstone, or Taupo would darken skies, cool climates, disrupt agriculture, and challenge modern civilization in ways we can barely imagine. The likelihood in any given century is low, but the consequences are high enough that scientists continue to monitor these systems closely. Preparing for such an event may seem impossible, but awareness is the first step toward resilience. Culturally, volcanoes will continue to inspire. They are symbols of resilience, of destruction, of creation. Artists, writers, and filmmakers will keep turning to their imagery, just as ancient storytellers once did. Spiritual traditions tied to volcanoes will endure, reshaping as communities evolve but never disappearing. And tourism, if managed with care, will keep drawing people to gaze into craters, to walk cooled lava fields, to feel the heat of Earth just beneath the surface. The greatest question, perhaps, is philosophical. What does it mean to live on a planet still alive? Volcanoes remind us that Earth is not static, not a stage built solely for human use, but a dynamic world with its own rhythms. They challenge the illusion of permanence. Cities may fall, fields may vanish, skies may darken, and yet, in time, life returns. Forests regrow on lava, new land rises from the sea, cultures rebuild in the shadow of fire. The future of volcanoes is not only about risk, but about renewal. As we look ahead, one truth is clear. Volcanoes will always be with us. They will continue to erupt to shape landscapes, to inspire myths, to alter climate. Our task is not to conquer them, but to learn, to adapt, and to live in harmony with their cycles. In this partnership lies the possibility of resilience, a future where humanity and volcanoes coexist not as enemies, but as neighbors on a restless planet. In the next part of our journey, we will step away from prediction and futurism to look at specific case studies. By examining volcanoes in detail, Etna, Kilauea, Pinatubo, and others, we will see how their unique stories illustrate the larger themes of creation, destruction, and renewal. To grasp the full story of volcanoes, it helps to step closer, to examine individual mountains and eruptions, each with its own character, history, and lessons. Case studies reveal the diversity of volcanic behavior, the ways local geology shapes eruptions, and the ways human communities respond. By looking at some of the world's most significant volcanoes, we see how universal themes of destruction and renewal play out in unique forms. Mount Etna in Sicily is one of the most active volcanoes on Earth. Towering above the Mediterranean, it has erupted for 500,000 years, shaping landscapes and cultures. Etna's activity is mostly effusive, producing steady lava flows that creep down its slopes. These flows destroy farms and villages, but also create fertile soils that sustain vineyards, orchards, and fields. Over time, Etna has become both menace and benefactor. For Sicilians, it is a presence woven into identity, a constant on the horizon, feared and revered. Etna teaches us about coexistence, how people can adapt to a volcano's rhythms, rebuilding and replanting in its shadow. Kilauea in Hawaii offers another story. For decades, it was in near constant eruption, its lava flowing into the sea. The eruptions were rarely explosive, but their persistence reshaped the island. New land formed as lava extended the coastline. Forests were buried, roads erased, neighborhoods consumed. Yet to many Hawaiians, these eruptions were not disasters, but natural processes, the visible work of Pele, the goddess of fire. Tourists traveled from around the world to witness lava pouring into the ocean, one of Earth's most spectacular sights. Kilauea reminds us that volcanoes are not always about sudden catastrophe. They can also be about gradual, relentless transformation. Mount Pinatubo in the Philippines tells a different tale. For centuries it slumbered, its peak forested, its danger forgotten. Then, in 1991, it awoke. Seismic swarms swelling and gas emissions warned of unrest. Scientists monitored closely, urging evacuation. When Pinatubo erupted, it produced one of the largest blasts of the 20th century. Ash and gas rose into the stratosphere, cooling the planet by 0.5 degree Celsius for 2 years. Locally, towns were buried, roofs collapsed, and tens of thousands were displaced. Yet, because warnings were heeded, tens of thousands of lives were saved. Pinatubo demonstrates the importance of modern volcanology, how science and preparation can turn potential catastrophe into survival. Mount Fuji in Japan illustrates the cultural dimension. Though it has not erupted since the early 18th century, its form dominates Japanese art, literature, and spirituality. Fuji is a stratovolcano, symmetrical and snow-capped, a symbol of beauty as much as of danger. Its slopes are sacred, climbed by pilgrims for centuries. In ukiyo-e prints, it appears as backdrop to everyday life, a reminder of nature's grandeur. Fuji shows that volcanoes are not only physical but cultural monuments, shaping identity as much as geology. Nevado del Ruiz in Colombia is remembered for tragedy. In 1985, its eruption melted glaciers, triggering lahars that swept down valleys. The town of Armero lay directly in their path. Despite warnings, evacuation was delayed, and more than 20,000 people died. The disaster became a symbol of miscommunication and unpreparedness. It also sparked reform, leading to better monitoring and stronger emergency systems worldwide. Ruiz reminds us that the deadliest eruptions are not always the largest, but those that catch societies unprepared. Eyjafjallajökull in Iceland shows how even small eruptions can have global consequences. In 2010, its explosive ash plume spread across Europe, grounding air travel for days. Millions of passengers were stranded, supply chains disrupted. No lives were lost, but the economic cost was immense. The eruption highlighted the interconnectedness of the modern world, where a volcano in one corner can ripple across continents. Eyjafjallajökull teaches us that hazard is not measured only in deaths but also in disruption, and that resilience must include not only evacuation but global systems. Yellowstone in the United States represents a different category, the supervolcano. Its vast caldera, stretching across Wyoming, is the scar of eruptions far larger than anything in recorded history. Though dormant for hundreds of thousands of years, Yellowstone remains active, with geysers, hot springs, and rising ground. Scientists study it closely, not because an eruption is imminent, the odds are exceedingly low, but because it represents the extreme end of volcanism. Yellowstone reminds us that Earth holds possibilities beyond our experience, forces that dwarf human history. These case studies, diverse as they are, share common threads. Each volcano reflects its geology. Effusive shields, explosive stratovolcanoes, catastrophic calderas. Each shapes human life through destruction, renewal, identity, or inspiration. Each teaches lessons, sometimes at great cost. Together they show the variety of volcanic behavior, the impossibility of generalization, the need to see each volcano as both universal and unique. In the next part of our journey, we will turn to the concept of resilience. How do societies live with volcanoes? What strategies, cultural, political, scientific, help communities adapt, prepare, and recover? From ancient rituals to modern evacuation plans, we will explore the many ways humanity has learned to coexist with fire. To live near a volcano is to live with uncertainty, yet for millions of people around the world, this is daily reality. They farm volcanic soils, build homes on slopes, and raise families in regions that may one day erupt. How do societies endure such risk? The answer lies in resilience, the capacity to adapt, prepare, and recover. Across history, communities have developed cultural practices, scientific systems, and political strategies that allow them to coexist with fire. In ancient times, resilience often took the form of ritual and myth. Communities offered sacrifices to gods believed to control volcanoes, hoping to appease them. In Hawaii, chants and offerings were made to Pele, seeking her favor. In Japan, shrines were built at the base of Mount Fuji, honoring its spirit. These practices did not prevent eruptions, but they provided psychological resilience, helping people make sense of catastrophe. Myths framed eruptions as part of a cosmic order, giving meaning to loss and guiding recovery. Practical strategies also emerged. Some communities learned to read signs of unrest, unusual smoke, rumbling, changes in springs, or animals' behavior. Oral traditions preserved these lessons, warning future generations. After the eruption of Mount Mazama, which created Crater Lake, native peoples in Oregon passed down stories of fire and destruction, ensuring that memory endured long after the event. Such traditions acted as early warning systems, embedding survival knowledge and culture. In the modern world, resilience has expanded into science and governance. Monitoring networks detect seismic activity, gas emissions, and ground deformation. Scientists interpret the data, issuing alerts. Governments prepare evacuation plans, train emergency responders, and build infrastructure designed to withstand ashfall or lahars. These systems save lives, but they depend on trust and communication. The tragedy of Armero in 1985 showed that warnings alone are not enough. People must believe them, and authorities must act swiftly. Resilience is not only technical, but social. Education is central. Communities that understand volcanic risks are more likely to prepare. In Japan, schools conduct evacuation drills for earthquakes and eruptions. In Indonesia, local villages participate in hazard mapping, identifying safe zones and escape routes. In Italy, citizens near Vesuvius are informed of risks and plans. Knowledge empowers, turning fear into readiness. Resilience also means rebuilding. After eruptions, communities face the challenge of recovery. Some relocate, abandoning slopes too dangerous to return to. Others rebuild in the same place, accepting the cycle of destruction and renewal. In Iceland, farms have been re-established on cooled lava fields. In Hawaii, homes rise again where lava once flowed. The decision to return reflects both necessity and identity, the deep ties people feel to volcanic landscapes. Volcanoes also inspire innovation. Engineers design roofs to withstand ashfall, bridges to resist lahars, and early warning sirens for tsunamis. Scientists develop models to predict lava flows, guiding where to build or not build. In some cases, humans even attempt to intervene directly. In Iceland in 1973, when lava threatened to engulf the harbor of Heimaey, firefighters sprayed seawater on the advancing flow, cooling and slowing it. The effort saved the harbor, preserving the town's economy. It was a rare example of humans successfully influencing volcanic forces. Resilience has economic dimensions too. Insurance, relief funds, and international aid help communities recover financially. Tourism, though risky, can provide income that offsets losses. Volcanic regions often market their danger as attraction, drawing visitors who wish to see fire and ash. The paradox is striking. The same forces that destroy homes bring travelers who sustain economies. Global cooperation strengthens resilience. Volcanic hazards cross borders. As ash clouds or climate effects spread, international networks share data, coordinate monitoring, and offer assistance. The Volcanic Ash Advisory Centers, for example, provide real-time information to aviation authorities worldwide. In this way, resilience is no longer local but global, built on shared knowledge. Yet resilience is never absolute. Volcanoes remain unpredictable, their power immense. No community is fully safe. The goal is not elimination of risk, but reduction of vulnerability. It is about living with volcanoes, not defeating them. And in this, humanity shows remarkable adaptability. For thousands of years, people have endured eruptions, rebuilt, and thrived again. Volcanoes test societies, but they also reveal strength. In the next part of our journey, we will explore the psychological and philosophical dimensions of volcanoes. Beyond survival, what do they mean to us as humans? Why do we climb them, paint them, revere them? What do they teach us about impermanence, power, and our place on Earth? Volcanoes are not only geological forces or natural hazards, they are also mirrors reflecting back to us questions about life, death, impermanence, and power. For thousands of years, humans have looked at erupting mountains not only with fear, but with wonder, awe, and even reverence. To understand volcanoes fully, we must step beyond science into psychology and philosophy, into the human response to Earth's fire. At the most basic level, volcanoes evoke awe because they reveal scale. To stand before an active volcano is to feel small, to sense forces far greater than ourselves. Lava fountains into the sky, ash clouds blot out the sun, pyroclastic flows race faster than any human can run. These are reminders that we are fragile creatures on a restless planet. Psychologists describe awe as a response to vastness that challenges our understanding. Volcanoes are awe-embodied, vast, powerful, incomprehensible in their energy. But awe is not only fear, it can also inspire humility, creativity, and connection. Many cultures see volcanoes as sacred, not just dangerous. The Japanese climb Mount Fuji not only as tourists, but as pilgrims, seeking spiritual fulfillment. Hawaiians honor Pele not only out of fear, but out of respect for her creative power. In the Andes, offerings are made to volcanic mountains seen as guardians. These traditions reflect a deeper truth, that humans seek meaning in forces beyond their control. Volcanoes remind us of our limits, but also of our capacity for reverence. Philosophically, volcanoes embody impermanence. They remind us that landscapes we consider eternal can change in an instant. A city that stood for centuries can vanish under ash in a single day. A coastline can be redrawn overnight. This impermanence can be terrifying, but it can also be liberating. It shows that change is the rule, not the exception. In Buddhist traditions, impermanence is a central teaching, and volcanoes are living demonstrations. They teach that nothing lasts forever, not mountains, not cities, not even civilizations. Volcanoes also symbolize creation. They destroy, but they also build. They bury fields, then enrich soils. They cover seas, then form islands. They erase, then renew. This cycle resonates with human experience. Endings followed by beginnings, loss followed by growth. Philosophers might see volcanoes as metaphors for transformation, for the way life itself emerges from chaos. They remind us that destruction and creation are not opposites but partners. On a psychological level, volcanoes also fascinate because they are thresholds. They are places where the hidden becomes visible. Magma, usually concealed in the deep earth, bursts forth. Energy stored for centuries is released in moments. Volcanoes reveal what is usually hidden, what is beneath the surface. For humans who are naturally curious about what lies beyond, whether beneath the sea, in the heavens, or in the self, volcanoes are irresistible. They are windows into the unknown. Art has long reflected this fascination. Painters depict volcanoes as sublime landscapes, glowing with fire. Writers use them as metaphors for passion, anger, or transformation. Poets describe eruptions as both terrifying and beautiful. In the Romantic era, artists saw volcanoes as symbols of the sublime, nature at its most overwhelming, beyond comprehension, both dangerous and inspiring. The imagery persists today, in films, literature, and music. Volcanoes remain powerful symbols in human imagination. There is also a psychological paradox. Many people are drawn to volcanoes, even in danger. Tourists flock to watch lava flows, to stand on crater rims, to hike volcanic trails. This attraction to risk reflects a desire to experience the rawness of nature, to feel alive in the face of danger. Psychologists call it edge work, the human urge to approach boundaries of safety. Volcanoes are perfect sites for such encounters, where danger is palpable but often manageable with caution. They remind us of mortality, but in ways that heighten life. Volcanoes also raise ethical questions. Should people live near them, knowing the risks? Should societies invest in monitoring every active volcano, even remote ones? Should resources be spent preparing for rare super eruptions? These questions force us to balance risk and reward, short-term needs and long-term safety. They reveal the complexity of human decision-making in the face of natural forces. Finally, volcanoes remind us of Earth's aliveness. They show that our planet is not a static backdrop, but a living system, dynamic and evolving. For philosophers who ponder our place in the cosmos, this is profound. It means we live not on a stage, but in a story, one still being written by forces older than humanity. Volcanoes connect us to that story, making us participants in a planetary drama. In the next part of our journey, we will return to science but with a broader view. We will explore how volcanoes connect to other Earth systems, tectonics, oceans, atmosphere, and even life itself. By seeing them in context, we will understand how they are not isolated phenomena, but threads woven into the fabric of the planet. Volcanoes cannot be understood in isolation. They are not separate curiosities scattered across the Earth, but vital nodes in a web of systems that link the deep mantle to the atmosphere, the oceans to the biosphere, and the surface to the core. To see volcanoes clearly is to see Earth as a single living planet, where every eruption ripples outward through interconnected processes. At the foundation is plate tectonics. Without moving plates, there would be no volcanoes as we know them. At divergent boundaries where plates pull apart, magma wells upward to fill the gap, creating new crust. This happens quietly, mile after mile, along the mid-ocean ridges, which together form the longest mountain chain on Earth, almost entirely hidden beneath the sea. Here, volcanism is steady, unending, the planet's conveyor belt of crust. At convergent boundaries, the process is more dramatic. One plate slides beneath another, carrying water and sediments deep into the mantle. Heat and pressure melt the subducted material, creating magma that rises to the surface. The result is volcanic arcs, chains of stratovolcanoes like the Andes, the Cascades, or the islands of Japan and Indonesia. These arcs are sites of explosive volcanism, where chemistry and pressure combine to produce some of the most dangerous eruptions known. Without subduction, there would be no Vesuvius, no Krakatoa, no Pinatubo. Then there are hot spots, plumes of heat rising from deep within the mantle. They punch through plates regardless of boundaries, creating chains of volcanoes as plates drift above them. The Hawaiian Islands trace such a path, each island once the site of eruptions, each now fading as a new island rises to take its place. Yellowstone, too, is thought to sit atop a hotspot, its vast caldera the surface mark of deeper processes. These hotspots remind us that Earth's heat is not uniform but focused, driving volcanism far from plate edges. Volcanoes also tie directly into the carbon cycle. They release carbon dioxide from the mantle, contributing to greenhouse warming. At the same time, volcanic rocks weather quickly, pulling carbon dioxide from the atmosphere and storing it in minerals. This push and pull, eruption and weathering, helps regulate Earth's climate over millions of years. Without it, our planet might swing between extremes of heat and cold. Volcanoes are part of the thermostat that keeps Earth habitable. Water, too, is inseparable from volcanism. Subduction carries ocean water into the mantle, where it lowers melting points and fuels magma. In turn, volcanoes release steam and water vapor, replenishing the atmosphere. On early Earth, much of the water in our oceans may have come from volcanic outgassing. Even today, each eruption is part of this ancient cycle. Water sinking, water rising, water reshaping the surface of the planet. The oceans bear the marks of volcanism in countless ways. Mid-ocean ridges, as constant volcanic factories, generate new seafloor and shape currents. Submarine eruptions release heat and minerals, influencing chemistry and ecosystems. Hydrothermal vents at ridge crests pour out metals and nutrients, sustaining life in the deep. Some scientists argue that these volcanic vents were the very cradle of life, offering the chemistry and stability necessary for the first cells. If true, then volcanism is not only a regulator of life, but its origin. The atmosphere is likewise bound to volcanic activity. Gases released during eruptions include carbon dioxide, sulfur dioxide, water vapor, and trace elements. These influence climate, rainfall, and even the color of sunsets. A major eruption can cool the planet by half a degree for years, altering weather patterns across continents. Tambora's eruption led to global famine. Pinatubo's cooled the planet in the early 1990s. At the same time, volcanic emissions replenish the atmosphere with carbon dioxide, ensuring photosynthesis continues. Without volcanoes, the balance of gases we depend on would falter. Volcanoes even connect to magnetism. Heat from Earth's interior drives convection in the liquid outer core, generating the magnetic field that shields us from solar radiation. While not volcanic in the surface sense, this deep geodynamo is part of the same energy that fuels eruptions. When we see lava erupt, we are seeing a surface echo of the same heat that powers Earth's shield in space. Life has evolved in concert with these systems. Plants thrive in volcanic soils rich in minerals. Animals adapt to landscapes reshaped by eruptions. Humans farm, build, and settle on slopes, drawn by fertility despite the risks. Cultures adapt to cycles of destruction and renewal. In this sense, volcanoes are part of the biosphere as much as the geosphere. They shape not only rocks, but lives. The connection extends beyond Earth. By studying volcanoes on Mars, Venus, Io, and Enceladus, we see how volcanism is universal, an outcome of planetary energy. On Earth, that energy ties into oceans, air, and life. Elsewhere, it may do the same. If life exists beyond Earth, it may be near volcanic vents on icy moons, sustained not by sunlight but by geothermal heat. Thus, to study volcanoes here is also to search for life elsewhere. Volcanoes are also teachers of balance. They reveal how tightly Earth's systems are coupled. An eruption does not stop at lava. It alters climate, reshapes land, redistributes carbon, feeds ecosystems, and challenges societies. Each eruption is a reminder that no system stands alone. To understand volcanoes is to understand interconnection, the threads binding rock to ocean, fire to sky, life to death. As we look at these connections, a picture emerges of Earth not as a static globe, but as a dynamic organism. Heat flows, plates shift, gases circulate, life adapts. Volcanoes are the visible pulse of this organism, sudden but rooted in deep cycles. They are signs that our planet is alive, restless, and evolving. In the next and final part of our journey, we will bring these threads together. We will reflect on what volcanoes teach us about science, about life, about resilience, and about our place on a planet that is still unfinished. And as always, we will close with a reminder of the role you play as a curious explorer of these stories and an invitation to continue the journey with us. Volcanoes are fire made visible, the restless heart of Earth revealed at the surface. Across this journey, we have seen them from every angle, as destroyers and creators, as hazards and resources, as myths and realities. We have followed magma from its birth deep in the mantle to its explosive release into the sky. We have walked among the ruins of Pompeii, watched skies darken after Tambora, and stood before the caldera of Yellowstone, humbled by its scale. We have seen how volcanoes shape continents, regulate climate, nourish soils, and perhaps even give rise to life itself. They are not simply mountains, they are processes, connections, and stories. Each eruption is an event, but also part of a cycle measured in millions of years. Each ash cloud is not only destruction, but also renewal. Each lava flow, once cooled, becomes the foundation of new land, new soil, new life. Volcanoes remind us that Earth is not static. It is alive. It is still being written. What do they teach us? They teach humility. To see a pyroclastic flow racing down a slope is to recognize that human strength, technology, and ambition are fragile against the forces of geology. They teach patience. Lava moves slowly. Landscapes shift gradually. Soil forms over centuries, processes that stretch beyond a human lifespan. They teach resilience. Communities destroyed by eruptions return, rebuild, and thrive again, drawing strength from the very slopes that once consumed them. And they teach connection. A plume of gas in Indonesia can cool crops in Europe. A fissure on the seafloor can feed creatures in the deep. A blast in Iceland can ground plains across the globe. Volcanoes are reminders that no part of Earth exists alone. Philosophers might say that volcanoes reveal impermanence. What we think is fixed, mountains, cities, coastlines, can change in an instant, but they also reveal continuity. For billions of years, volcanoes have erupted, and for billions more, they will continue. Long after our civilizations fade, volcanoes will still shape Earth. They are the guardians of deep time, marking the passage of eons. For scientists, volcanoes are both challenge and inspiration. Each eruption is a puzzle, each mountain a laboratory. Seismographs, satellites, drones, and models are all attempts to listen to Earth's voice, to predict its next breath. We are learning, but we will never fully master them. Volcanoes are too complex, too vast, too ancient, and perhaps that is part of their value. They remind us that mystery still exists, that some forces remain beyond full human grasp. For artists and storytellers, volcanoes are symbols. They stand for passion, destruction, transformation, renewal. They appear in myths, novels, paintings, and films, always larger than life. They inspire awe not only in those who live nearby, but in anyone who has looked at their glowing slopes or towering plumes. They are metaphors for the human condition, for our own cycles of destruction and rebirth. For communities who live in their shadows, volcanoes are family. They provide fertile soils, fresh water, geothermal heat. They demand respect, sometimes fear, sometimes reverence. But they are part of daily life, part of identity. Children grow up under their slopes, farmers plant in their soils, pilgrims climb their peaks. The relationship is intimate, complicated, enduring. And for all of us, volcanoes are reminders of our place on this planet. We are not separate from Earth, but part of it. The air we breathe, the land we live on, the food we eat, all shaped in part by volcanic processes. To understand volcanoes is to understand ourselves, because we are products of the same Earth that erupts, quakes, and reshapes itself. So, as we close this journey, consider what volcanoes mean to you. Are they terrifying, inspiring, both? Perhaps they remind you of a story you've heard, a place you've visited, or an image that has stayed in your mind. Perhaps they remind you of resilience, of change, of the vastness of time. Whatever they mean, volcanoes are part of the human story and part of the Earth's story, a story still unfolding. And as always, I'd love to hear your thoughts. Which volcano fascinates you most? Which eruption or story stayed with you? Share it in the comments below. Your reflections are part of this ongoing conversation. And if you've enjoyed this deep journey into the forces that shape our planet, don't forget to subscribe so you'll be with us for the next exploration into the mysteries of science, history, and the world we share. Because the story doesn't end here. The Earth will keep erupting, shaping, creating, and destroying, and together we will keep exploring.